Hello. The last topic that we're going to look at here in Chapter 2 is acids, bases, and pH. Okay, acids, bases, and salts. We have this term dissociate. Dissociate means to split. So, HOH, in other words, water, oxygen, 2 hydrogens. This is going to split, and it's going to split into a hydrogen ion, this hydrogen with a positive charge, and what's called a hydroxide ion, this OH group with a negative charge. Now, in a container of water, there's going to be very few of these molecules that are split this way. About 1 times the portion of molecules that are split are going to be about 1 times 10 to the negative 7th power of these molecules will be split in this manner. Okay? But an acid, we use this term dissociate to look at the idea of an acid or a base. An acid, and again, notice this is in red, so you're probably going to see this again on the test. An acid is a substance that dissociates and releases hydrogen ions. So here's the acid, hydrochloric acid. Now what makes it an acid is that when this is dissolved in water, it dissociates or it splits and it releases hydrogen ions. Now it also releases these chloride ions, but it's the release of the hydrogen ions that make this substance an acid. Okay, a base is a substance that when it's dissolved in water, it dissociates and it releases hydroxide ions. Now a base can also do something else. A base can be a substance that accepts hydrogen ions and thus reduces the number of hydrogen ions in solution. So we've got sodium hydroxide. When this is dissolved in water, it splits into sodium ions and hydroxide ions. Thus it's a base. Now here's ammonia, NH3. Now there's no OH group to release, but this acts as a base. When ammonia is dissolved in water, it will actually steal a hydrogen off the water molecules, and the NH, that's supposed to be subscript 4 there, as a positive ion, and then leave these OH ions left over from the water. The other thing that ammonia can do, if there are hydrogen ions floating around here in the water, it can scarf up those hydrogen ions and pull those out of solution. Okay? Now we've got pH. pH is a measure of the acidity or alkalinity of a solution. And if you're mathematically inclined, pH is the negative log of the hydrogen ion concentration. This H plus in brackets, what that means is the concentration of hydrogen ions in terms of moles per liter. Okay? So the pH, looking at the pH scale, the range of the pH is from 0 to 14. If we have a pH below 7, it's an acid, and we have more hydrogen ions than hydroxides. If we have a pH equal to 7, it's neutral, and the hydrogen ion concentration is equal to the hydroxide concentration. If we have pH above 7, that's a base, and the hydrogen ion concentration is less than the hydroxide concentration. Okay, so let's see if we can look at this using a little box diagram. So I'm going to try to draw this. It may be a little sloppy, but we'll see how it goes. So, let's see, tools, let's make a box right here. That'd be a good start. Okay, then I want to put a line through here. I'm going to put a diagonal line right there. And Okay, thought there was a place I could type here, so I'll just have to draw it. So what we have here, this is the hydrogen ion concentration represented in this box. It's supposed to be a plus sign. Over here is the hydroxide concentration. Okay. With a negative, that's supposed to be a negative. Got a little carried away with it. Okay. So we've got our pH values of 0. Right in the middle here is 7. And down up at this end, 14. Okay. Now, right here, there's supposed to be a dotted line coming down there. And right there at pH of 7, the amount of hydrogen ions is equal to the amount of hydroxides. Down here in the acid range, I'm just going to put an A for acid right there. Down here in the acid range, we have an abundance of hydrogen ions, more hydrogens than hydroxides. The stronger the acid, more hydrogens we have. Here in the base part of the range, we have more hydroxides than hydrogens, and the stronger the base, the more hydroxides we have, the fewer hydrogens we have. Okay. Okay, so here's some examples of different common everyday materials and their pH. And this diagram is found in your textbook. Okay, now this is a little bit complicated looking, but it explains the pH values and where those pH values come from. And so let's take a look at it here. So we've got our pH 0, 1, 2, 3, 4, 5, and we could go on up to 14. Now these numbers relate to something. They relate to the moles of hydrogen ions per liter of solution. So with pH of 0, we have 1 times 10 to the 0 power. pH of 1, it's 1 times 10 to the negative 1 moles of hydrogen ions per liter. 1 times 2 to the negative 2 moles of hydrogen ions per liter for pH 2. And then, of course, if we take those from exponents to more everyday numbers that we're used to working with, here's what we'd have in moles of hydrogen ions per liter of solution. So this is why the scale seems backwards. We go to a lower numeric value on this pH scale, but we have more of what we are measuring, more hydrogen ions per liter of solution. Okay. Now, because these numbers on the pH scale come from powers of 10, what we see is that a 1 unit change in pH is a 10-fold change in hydrogen ion concentration, thus a 10-fold change in acidity. So if we have a solution that is pH 4, pH 5, that's a terrible looking 5, pH 6, and pH 7. Okay, so we go from here to here. This is a factor of 10. The solution that is pH 6 is 10 times more acidic than pH 7. It has 10 times more hydrogen ions. We go from 6 to 5. Again, it's a factor of 10. The solution that is pH 5 is 10 times more acidic than the solution that's pH 6. 10 times more hydrogen ions. Now, a 2-unit change, notice we are multiplying. We are not adding. So, that is a factor of 100. The solution that is pH 5 is 100 times more acidic than the solution that's pH 7. Okie dokie. What if we have a 3-unit change in pH? Again, we're multiplying. 10 times 10 times 10. Solution that is pH 4 is 1,000 times more acidic than the solution that is pH 7. So, a small change on that pH scale is in reality a large change in acidity. Okay, let's look at this term buffer. A buffer is a substance that resists pH change. It maintains a stable pH. Notice with a couple of asterisks on it right here, fluids in living organisms tend to be buffered. This is another example of homeostasis, the tendency to maintain constant internal conditions. We don't have wild fluctuations in pH in the fluids in our body or the fluids in a tree or even in a single cell microorganism. They tend to be buffered, maintain stable pH. Now, here's an example. pH of our blood is about 7.4, give or take about 0.05 of a pH unit. And this works because in the blood we have CO2, carbon dioxide, dissolved in water, and that forms this, carbonic acid. This carbonic acid dissociates to form hydrogen ions and bicarbonate ion. Now, if something's going on that's adding more hydrogen ions to our blood, trying to make it more acidic, it's going to push this reaction back to the left and tie up those hydrogen ions in carbonic acid and then cause that to release carbon dioxide. If something's going on that's pulling hydrogen ions out of our blood, trying to make it more basic, then more of this carbonic acid will dissociate, releasing hydrogen ions. So it's a balancing act, and that's what keeps the pH stable. Okay, a buffer is a weak acid or a weak base. Now, weak means it only partially dissociates. So if we go back here, not every bit of this carbonic acid dissociates to these ions. Some of it is always held in reserve. A strong acid would completely dissociate. So weak acid, weak base does not mean dilute. It means that it partially dissociates. Another thing we see is that if we combine an acid plus a base, they neutralize each other. We get a salt plus water. So here's hydrochloric acid, sodium hydroxide. It forms table salt, sodium chloride plus water. And a salt is a compound formed when the hydrogen ion of an acid is replaced by some other cation. So here's the hydrogen ion of an acid, and we replace that with this cation right here of sodium, and that forms this salt of table salt. And these salts provide the minerals that we require. Okay, well, that wraps up chapter 2, and hopefully you're getting something out of these videos. I'll go over this with you again in class, probably just quickly, not in a whole lot of detail. So long.